Okay, so we are moving right along, and on Tuesday we covered the normal distribution. We covered sampling distributions. I'm sorry, not sampling distributions, the binomial distribution and the normal distribution. And today we will take a look at sampling distributions. So as we get into that, it's useful for us to kind of just review exactly what a sample is and what we mean by that. And so again, one of the big ideas in statistics is that we want to make conclusions about the population being everybody who is relevant to answering the research question of interest. And the problem is that this population is always too big for us to study directly. So what we have to do instead is we look at a sample, we look at a small selection taken from the population. And ideally what we want is we want our sample to be like a miniature version. We want it to be representative of the population. And when we do that, that forms our observed data. And based on the data that we get from our sample, we try to make inferences about the population. And so, when we're looking, when we're trying to describe the population, and when we try to describe our sample, we'll, use terms like, the mean of the population is this, and the mean of the sample is this, and the standard deviation is this, and the standard deviation is that, and et cetera, this and that, and this and that. In order to kind of distinguish between, are you talking about the mean of the population or the mean of the sample? We call these summary statistics, numeric summaries of the population, we call those parameters, and we call numeric summaries of the sample a statistic. All right, and that's kind of where the name of the subject itself comes from. It comes from, I don't know. Actually, I don't know what the etymology of statistic is, but we do use that term statistic as far as, when we're talking about summarizing some properties of the sample, okay? So statistics apply to samples and parameters apply to the population. And statistical inference, which is kind of this process that we're gonna get into, is the idea of taking the statistic from a sample to then make conclusions about the corresponding parameter in the population. So here's an example. Let's say, some political poll is conducted, and we say, there's a sample of 800 likely voters. Okay, so whatever election is coming up, we can say, the population is going to be all likely voters in the entire population, but we can't survey all the voters. So our polling institute or whatever was able to survey 800 people. And so when we surveyed our sample, let's say the sample ends up with a sample proportion of say 44%, 44% support candidate John Q. Public, whoever we're talking about, right? So and then so what that would be, that 44% is a statistic. That's a sample proportion. And what we want to do is we want to say, okay, if the sample has 44, excuse me, 44%, excuse me. All right, if 44% of our sample supports this candidate, then what can we say about the general population? What's the proportion of all voters who are going to vote for this candidate? Is that going to be enough to win the election or something like that? Another example is maybe there's a medical experiment on blood pressure medication. Sorry. My voice is giving me all sorts of trouble today. And so we have a sample of, say, 50 volunteers with high blood pressure. And so our population is going to be everybody with high blood pressure who might take some medication. And so we do some kind of controlled experiment. We give some people the placebo, some people the actual medicine. And at the end of the experiment, we get these statistics. We say the mean blood pressure in our sample for patients who took the medication is 125. The blood pressure for the patients who got placebo, our sample is 135, right? We're looking at our sample. These are the people who participate in our experiment. And we're hoping to make conclusions that generalize to the general population, which is everybody who maybe has high blood pressure. And so what we want to do is we want to make conclusions about the parameter, which is going to be kind of the difference between those who take the medication and those who take placebo. And so, as you're writing things out, we use different symbols to kind of distinguish between sample values and population values. So the sample mean will be y bar or x bar, whereas the population mean is mu. This is the Greek letter. Looks kind of like the letter U, but with a little tail in the front. This standard deviation is S, and the population standard deviation is sigma. The sample proportion is P with a little cap on it. This is called P hat, and the population proportion is P. All right, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is C as in cat. Okay. So we talked about simple random sampling and sampling process back, I think, in our first lecture. And we said it's not guaranteed to produce a representative sample, but it should. And we're going to use, and we're going to assume the samples that we produce, as far as the rest of our problems and things like that go, we're going to assume that they are generated via simple random sampling. That's maybe not a good assumption. In reality, it's difficult to pull off a good simple random sample, but we're going to just kind of assume that this is what's working for us. Okay. So when we do a simple random sample, the individuals, excuse me, I'm okay. I'm alive and well. I don't just something's going on with my throat. All right. So because it's random, statistics that we get from a sample are going to vary from one sample to another. So if one person takes a random sample and we calculate the mean of the sample, we expect the mean of our sample to be close, but not necessarily exactly equal to the mean of the population, right? So let's say we have a population, follows a normal distribution. The mean of the population is 16, has a standard deviation of 5 or whatever. And then what we're going to do is we're going to take a random sample from this population, maybe like 5 values from the population. And we're going to calculate the mean of our sample. When we do that, the mean of our sample, we expect it to be kind of close to 16, but not necessarily exactly equal to 16. Okay. And the idea is that, you know, if we took a ton of observations from the population, like thousands of them or something, then the mean of our sample should approach 16 in the long run. And the standard deviation of our sample should also approach kind of 5. And, you know, we said the, you know, when you draw individual values, and we said, you know, according to the normal distribution, if the standard deviation is 5, then around 95% of them will be between 2 standard deviations of the mean. And if the mean is 16 and the standard deviation is 5, 2 standard deviations within the mean would be going up 10 or down 10, so between 6 and 26. But when we take samples of 5 values, we expect the sample mean to be close to 16, which is that population mean, but we don't expect it to be exactly equal to it. So, you know, when we do this, we expect some sample means to be more probable than others, right? So if the population has a mean of 16 and I take 5 random values, could I get a sample mean that's, say, 15? And I think we would say, yeah, that sounds pretty likely. Okay. What about a mean where a sample where the mean of the 5 values is only 13? All right, we say, well, that could happen too. Probably not as often as getting 15. Could we take 5 values from this population? Again, the mean of the population is 16. Could I get 5 values where the mean of those 5 values will end up being 10? And we go, it sounds unlikely. What about a mean where a sample where the mean of the 5 values is 8, okay? Or a sample where the mean of the 5 values is 3, right? And again, the population has a mean of 16, and, you know, 95% of the values are between 6 and 26, but, you know, technically some of the values might be less than 6. And is it possible that to get all 5 values such that the mean of all 5 values is 3? And we're going to say, you know, it's not impossible, but it seems like that's incredibly unlikely. And so while these different outcomes are theoretically possible, kind of intuitively, I think we get the sense that, you know, these outcomes where the mean has where the sample has a mean of 8 or the sample has a mean of 3, those sound like those really shouldn't happen that often in life, okay? And so what we're getting at is this concept of a sampling distribution. And the sampling distribution is going to be the distribution of the possible sample statistics. Like, what can we get for a mean of a sample? And so I'll just read this. The sampling distribution shows us the probability that a random sample of a certain size produces a particular value of the sample statistic. So in our case, we're going to be looking at, say, the mean of a sample, y bar, and we're going to look at the sampling distribution of y bar. And what we can do is we can kind of simulate this using this little app, web app, okay? And so what we're going to see is there's, at the top, we've got something that represents the population. And what I'm going to do is I'm going to repeatedly draw a random sample of a particular size from that population. So I'm going to draw a little piece, a sample from the population. From that sample, I'm going to calculate the mean of the sample, y bar, okay? And I'm going to kind of tally it. And then I'm going to do this again, and I'm going to take another sample of the same size. We're going to calculate y bar. I'm going to do this again. and again. And I'm going to just do this over and over and over and over again. I'm going to repeat this thousands of times. Every single time, I'm going to keep track of the sample mean y bar that I get from every sample that I select. And then, and what we'll see is we'll end up getting kind of this simulated sampling distribution. We'll see certain y bars are likely to appear, other y bars are less likely to appear. So I'm going to go ahead and click this link. And this is what it looks like. So this here represents my population. This population has a mean of 16, a standard deviation of 5. Okay, and I'm going to take samples of size 5. And first, I'm going to just do a few animated examples. Okay, so here I'm drawing 5 values from this population. What we're going to see when I draw 5 values is that most of the time we're going to get values close to the middle, and sometimes we'll get values out here and values down here. And almost never, you'll almost never see a value all the way at the end or all the way at this end. You might see a couple values close there every now and then, but by and large, most of our values are going to be kind of in this middle region. And so here are my 5 values. And if I take the mean of these 5 values, it's going to be right here. Let me do this again. 5 values, I take the mean, it drops down there. Another 5 values, I calculate the mean and it drops down there. And I do this over and over and over again. Just take 5 values, calculate the mean. Oh, we did get one extreme value, and I said this should almost never happen, but it did. And we calculate the mean, and it drops down there. Excuse me. Okay, so I can do this over and over again, and I can just kind of speed this up, and I can say, you know what, let's just do 5 samples of 5 at a time. In here, we're kind of rapidly building this up. And this can get tiresome and tedious. So I'm going to go ahead and just kind of click. All right, what would happen if I just do, so this is after, now it says like 304 repetitions. I wish there was like 100, but let's just go ahead and do it 10,000. All right, so this is after, say, 40,000 repetitions. This ends up being the distribution of different kind of sample means, okay? So again, each time we've calculated we've drawn a random sample of 5 values, and we dropped a sample mean into our sampling distribution. And so what we see is that, you know, values near the center, 15, 16, 17, those happen frequently. And it looks like never do we get a mean or a sample where the mean is like 3, or a sample where the mean is like 25. You know, we might have gotten, what is it, 16, 17, 18, 19, 20, 21, and maybe the highest we get is a sample where the mean is like 22, but that seems to be a pretty rare occurrence. Okay, what would happen if I take a larger sample? So let's say I take samples of size 16. Okay, with a sample of size 16, I draw a much bigger sample and I calculate the mean, and it drops down right here. We do this again. Another big sample of 16, calculate the mean, it drops down there. Random sample of 16 values, it takes a lot. Okay, and so what do you think the, so I can do, you know, 5 at a time. What do you think the resulting distribution would look like if I go ahead and click this 10,000 button? Well, this is what it looks like. All right. So let's just do a quick comparison. So when we had n equal to 5, it looked like this. With n equal to 16, it looks like this. And if I go up to n equal to 25, it looks like that. Okay, it's a little bit difficult, but what we see is that with smaller samples, with n equal to 2, you get the resulting sampling distribution is wider. And as I increase my sample size, n equal to 5, n equal to 10, n equal to 16, n equal to 20, and n equal to 25, the resulting sampling distribution gets a little bit skinnier. Okay, I think I got that. So this is kind of what we see, and the app actually shows kind of the standard deviation of the resulting sampling distribution. Here, standard deviation is 1. With n equal to 2, the standard deviation is 3.53. N equal to 5, the standard deviation is 2.24. And this is kind of summarized here. Okay. So what's happening? Well, when you have, say, a sample of size 2, it's not that weird to get, just by random chance, to get 2 people who are, let's say this is like heights or something, 2 people who are really tall, and the average of those two people's heights is very high, or 2 people who are really short, and the average of those 2 people's heights is very low. But if you take a sample of, say, 16 people, it would be really hard to get all 16 people such that the average of all 16 would have a height that's really high, or a sample where the average of all 16 people have an average height that's really low. Because most likely to happen is you might get 2 or 3 people in your sample who are really tall, or 2 or 3 people who are really short, but probably most of the other people are not going to be these extreme values. They might be, somewhere closer to the middle. And so when you take the average of everybody, that average value is going to be kind of closer to the middle. So when you have a small sample size, it's not going to happen very often, but it will happen where you get kind of 2 people where their average is very high, or 2 people where their average is very low. But then taking 16 people, it's going to be much more difficult for all 16 people to end up having an average that ends up being very high, or all 16 people having an average that ends up being very low. So what you end up having is, when you have a big sample, most of the values tend to be close to the middle, tend to be close to the mean, whereas when you have a smaller sample, you can end up having a little bit more spread. Okay, we can actually simulate more sampling distributions, not just a normal distribution. And so this app actually allows us to simulate, say, a uniform distribution, but it only allows us to, say, look at samples of size 2 or 5. And I kind of wanted to show, samples of different sizes. So if I take samples of size 2, okay, where this is the parent population, meaning that all values, this is a uniform distribution. This says all values 0 and 32. These are just as likely as 15 and 16 and things like that. Whereas with the normal distribution, only values near the middle had a very high probability, and values way out here were very low probability. Here we're going to say all values equally probable, okay? I'm going to just take 2 at a time. So if we do this over and over and over again, I think the resulting distribution, anybody want to guess what the resulting distribution is going to look like when for the sampling distribution? I think it'll be a surprise for most of you. So if I do this over and over and over again, the resulting distribution looks like a triangle. Okay, you get this kind of pyramid-looking thing, and so it feels like a bit of a surprise, but it's also not too surprising, because if we say, how many ways are there to get an average of 16? if your values go from 0 to 32, there's going to be 32 ways. You can do 0 plus 32, 1 and 31, 2 and 30, 3 and 29, so on and so forth. And if you take those, there's going to be, I think, 32 ways or 33 ways to get an average of 16. How many ways are there to get an average of, say, 16.5? Okay. If there's 33 ways to get an average of 16.16, there's 32 ways to get an average of 16.5. You need to get 0 and 31, 1 and 30, 2 and 29, and there would be a total of 32 ways. How many ways are there to get an average of 17? It'll be one less than that. You can get average, what did I say? Average of 16.5, I'm sorry, would be 1 and 32, 2 and 31. Okay, average of 17 would be 2 and 32, 3 and 31, 4 and, I can't do math, 4 and 30, 5 and 29, and so on and so forth. And if you can list them all out and you'd say, oh, okay, how many ways are there to get a certain average value, the mean, and it would be kind of linear. How many ways are there to get an average of 32? There's only one way. Both of the numbers that you draw have to be 32. And so you end up getting this triangle distribution. Okay. Let me show you kind of what this would look like with a whole bunch of simulations here in R. Where did this go? Here we go. All right, let's run this. Okay, so we're going to create a uniform population. We're going to start off, I'll start off with samples of size 2. And here's kind of the resulting sampling distribution. These are all the sampling means, and we get this triangle, okay? Here, let's try samples of size 3. Okay, samples of size 3, we get a little bit of kind of curvature here. With samples of size 4, it looks like that. Samples of size 5, and we get something that looks like this. Samples of size 6, it looks like that, and I probably do this. Size 6, okay. So you know what, let's put this inside a loop. Wipe all this out. Two through, let's do 20. Sorry, doing a little bit of stuff here. Okay, we'll do this, make a whole bunch of graphs. Oh, please work. Okay, I might have broken something here. I did this wrong. I could, okay, stop. Sorry. I put this in the wrong part of the loop. Okay, this will work now. Let's wipe everything out, clear everything. Okay, sorry. Here we go. I think. Okay, samples of size 2. samples of size 3, samples of size 4. It's showing up on my screen. Is it showing up for you guys? Okay, okay. Samples of size 6, samples of size 7, 8, 9, and we kind of get a similar phenomenon where as we increase the size of our sample, the resulting distribution ends up getting, oh, we're getting some weird things happening there, but okay. And so, you know, as I kind of cycle back through here, we can see that as the sample size decreases, the spread gets wider, and as the sample size increases, the spreads decrease, okay? Let me do, let's try this, all right? So here is, let's do a dichotomous population, okay? And so let me just show you what happens with a sample of size 1. So with this is like a strange artifact, but here basically what I'm trying to illustrate here is you can actually, on this thing, you can actually say, you know, I only want values that come from this lower end or the upper end, right? And so if I do this and I animate this, I can get 2 values from the lower end, 1 value from the lower and 1 value from the upper. I'm just waiting for something where both of them get drawn from the upper side. It'll happen eventually. It's got a 25% probability. Okay, there we go. Both from the upper, right? So we can get both from the lower end and we get a mean down here, 1 from up here and 1 from down here, where the mean ends up in the middle, and then we can get the possibility where both come from up here and we get a mean up here. And if we take the average, we're going to get some kind of distribution where we end up getting kind of 3 peaks that look like this. Okay, so I can say, you know, if I take samples of size 2, here it is where I get kind of 2 peaks here. And again, I kind of want to show you what's going to happen if I try out samples of a whole bunch of different size. So here we're going to go samples of size 2 all the way up through samples of size 20. So samples of size 3, I end up getting kind of 4 peaks, samples of size 4, size 5, and this is what it ends up looking like. So these are sampling distributions when we take different sized samples. 19, 20. Let me do a few more. We'll go from 21 to say 20, 25. And eventually what happens is when your samples get large enough, you end up getting something that looks kind of like the normal distribution, okay? So even though we started off, you know, with samples of size, you know, 2 and 3, these just look kind of like crazy things where we have a bunch of peaks and stuff like that. As we work up our sample sizes, what we see is the amount of spread in our sampling distribution shrinks, and the overall shape looks a lot like the normal distribution. You get this kind of bell-shaped curve. All right. So this is what I was trying to, this is what these slides are trying to illustrate, is that, you know, even if your population is uniform, even if your population is kind of dichotomous and you get all of these crazy size shapes, eventually with large sample sizes, the result ends up looking normal. okay? And that's kind of one of the big key ideas in today's lecture is that the mean of the sampling distribution, when we look at it, is going to be equal to the mean of the population mean. And another thing is that as the sample size increases, the standard deviation of the sampling distribution, the spread that we see in these graphs will shrink, okay? We give that name, a special name, the standard error. Standard error is the spread in our sampling distribution, or the standard deviation of our sampling distribution. And the formula for that is sigma divided by the square root of n, okay? Sigma being the population standard deviation divided by the square root of your sample size. And what perhaps one of the most interesting things is that the shape of this sampling distribution eventually becomes normal despite the population having some crazy shape, right? It's not always normal, right? We would not say that this has a normal shape. This looks quite different from normal. But as the sample size increases, and 25 is kind of like the rule of thumb here. When you say, when your sample size gets big enough, sample size of 25, we'll say, yeah, it's probably going to look like a normal distribution. So this is known as the central limit theorem. We're going to have just kind of this loose definition of the central limit theorem. If you were to like major in statistics or something, you would have a much more formal and rigorous definition of the central limit theorem. But for this intro class, this is good enough. And the central limit theorem says that, no matter what kind of distribution the population looks like, if your sample size is large enough, then the sampling distribution of y bar, that is the sampling distribution of the sample mean, can be approximated with a normal distribution. And so what do we mean by large enough? Well, if the population is normal, then any sample size is large enough. And we kind of saw that, I think, in one of these earlier slides. This one here is that, when our population, the parent population is normal, even with samples of size 2 or samples of size 5, the resulting distribution looks like the normal distribution. When we had a population that was not normal, like the uniform or a dichotomous population, we needed bigger sample sizes. In general, a sample size of 25 is going to be large enough for most cases, but if you have something that's very skewed, then a sample of size 25 won't be big enough, okay? There's also kind of a flip side. You don't want your sample to be so big that you're sampling too much of your population. This is rarely a problem, but it could be an issue that you run into. So let's try out a problem here, okay? We're going to say the pulse rates of adult women in the United States are approximately normally distributed with a mean of 74 beats per minute, standard deviation of 13 beats per minute, okay? Again, this is like just made up information, so don't hold me to it. All right, so if we select a random sample of, say, 36 women, what is the probability that the mean pulse rate of the entire sample is under 71 beats per minute? Okay. So to answer this question, we're going to start by saying, just kind of stating the values that we do know. We know n is equal to 36. We know that the mean mu is equal to 74. We know that sigma is equal to 13. And we want to know what's the probability that the mean of a sample y bar is going to be less than, say, 71. Okay, and so we can apply the central limit theorem because our sample is large enough. It's 36. We also know that the population is normal, so actually really any sample size would have been big enough. Okay, so the first thing is we're going to say, all right, if we, what is the sampling distribution of y bar? And using the central limit theorem, we're going to say that the mean is equal to 74. That's the population mean, 74. And then the standard deviation, we don't want to just use 13. We have to do 13 divided by the square root of n. So we're going to do 13 divided by the square root of 36. We're going to get the standard deviation of 2.167. So let me pull up my tablet here. And so this just becomes a regular normal distribution problem. And we're going to say, sorry. All right, so we got 74 right here. We want to know what's the probability of being at 71 or lower. And we have y bar coming from the normal distribution where the mean is 74. And the standard deviation is 2.167. Okay, so we're going to say the z-score, 71 minus 74 divided by 2.167. This is something, negative 1.38. Okay. All right, and then we go to our reference table. All right, so where is negative 1.38, 0.0838, 0.0838. Okay, so from the table. Okay, that's going to be our answer. Okay, so we're going to say if we take a random sample of 36 adult women, there's around an 8% probability that the mean pulse rate of this exact sample, this particular sample, will be 71 or lower. Okay, and so the key here is just remembering that the standard error is going to be sigma divided by the square root of n. Okay, let's see. All right, let me go ahead and give you, why don't you guys just try this first one out, okay? So we'll say the partial pressure of oxygen is this, where the mean is this, standard deviation is this. We're going to take a sample size of 25, and we'll just want you guys to take a minute and try out this first problem. What's the probability that the sample average will be greater than 36? All right, so let's go ahead and take a look at how do we would get this, the answer to this. So we said the values have a mean of 38, standard deviation of 9, and we're taking samples of size 25. Okay. So according to this and the central limit theorem, we're going to say y bar comes from a normal distribution where the mean is going to be 38, and the standard deviation, though, our standard error, is going to be sigma divided by the square root of n. So we're going to have 9 divided by the square root of 25. 9 over 5 is what, 1.8? Okay. And so now we're asking, what is the probability that the sample average will be greater than 36? Okay, so the mean is 38. We want to see, okay, 36 and greater. So we're going to see is going to be 36 minus 38 divided by 1.8. Negative 1.11. Okay, and then we're going to go to our z table, and we're going to find the area to the left of negative 1.11 from our z table is 0.1335. That's the area to the left. The table always gives us the area to the left. So we want the area to the right, which is going to be 1 minus that. And so the probability that z is greater than negative 1.11, this is the probability that y bar is going to be greater than 36. That's going to be 1 minus 0.1335, which is going to be 0.8665. That should be our answer. Okay. Is that good? Good with everybody? All right, great. Okay, and then you can do this one on your own. Greater than 41, same idea, just a different number. Okay, all right, we'll keep going. And now I'm going to introduce this concept of confidence intervals. Before I do that, let me go ahead and give you your second view quiz answer. Second view quiz answer for today is D. D as in dog. D as in dog is your second view quiz answer. D as in dog. Okay. So, you know, we talked about sampling distributions, but the goal is that we want to be able to look at a sample and make conclusions about the population. So here's just kind of a silly scenario. This is coming from the textbook, and it says, you know, what if we caught some butterflies, right? And I don't know why we're doing this, but we're going to try to calculate the area of the wings of the butterflies. And so you know, I don't know how you do this, but I guess you capture the butterfly and then you put them out on a piece of graph paper or something, and then you trace them and you say, all right, this is the area of the wings or something. Some people might be into this, and this is an example from the textbook, but we're going to say we got 16 random butterflies. I don't even know if that's even physically possible. Random butterflies, like, how do you know? Okay, well, anyway, we're going to forget the logistics of the troubles of getting a random sample of butterflies, because I don't think this is actually physically possible. Because, you know, you can go to the forest and you can try to catch some butterflies, but they're not random. They're just like the locally present butterflies, and they're not actually like representative of all butterflies in the world or something. But okay, but anyway, that aside, we're going to say, all right, here's my sample. And we're going to just say, just to keep it simple, we're going to say the sample, the average of these 16 butterflies, 30 square centimeters. Okay, so I guess you got this, like, this wing and this wing is average wing area is 30 square centimeters. So what does this tell us about all butterflies, all monarch butterflies, all of this particular species? Do you guys remember when there was like that huge butterfly migration like a couple of years ago? No, there's like a huge butterfly migration, and every time I got in the car, I was so scared because I always felt bad. Like at the end of the drive, like the front of my car was just covered with like poor butterflies that didn't get out of the way in time. And I was like, oh gosh, but okay, I'm glad some people remember. Oh my gosh, yes. All right, great. Okay, so anyway, the idea here is if my sample has a mean of 30, does that mean the population mean is also equal to 30? And I think our answer would be like, well, probably close to 30, but I wouldn't expect it to be exactly equal to 30, okay? And so maybe instead of saying, you know, the population is going to be exactly this value, we can say, you know, I think the population is going to be within some range, maybe like 29 to 31 or 28 to 32 or something like that. That's kind of what we want to do, all right? So put that thought on hold and behold my beautiful artwork here. This is going to be a silly analogy. This is a picture of a dog on a football field, okay? And this dog is at the 30-yard line of the football field, okay? But more impressive about this dog is that the dog's owner is also in this picture. except the dog's owner is an invisible man, okay? It's an invisible owner, and there's an elastic leash that's also invisible. Just, I know it's ridiculous, just go with it, okay? And the question is, where is the owner? Where is the owner of this dog? Okay, so we see the dog at 30, but where's the owner? We don't know, right? So we don't know, so that's kind of the key. We don't know the exact location of the owner, but overall, because they're going on a walk together and there's a leash that kind of holds them together, we expect the owner to be close to the dog. That's kind of the premise. So if we see the dog at the 30, we expect the owner to be close by. Furthermore, we have carefully studied the behavior of the dog and the owner together. And we've come to these, we know these facts about the dog and the owner. So the dog generally likes to stay close to the owner. It doesn't like to pull against the elastic leash. It's a good dog, right? Just like all dogs are. And 68% of the time, what a specific number, the dog stays within 1 yard of the owner. 95% of the time, the dog stays within 2 yards of the owner. And you guessed it, 99.7% of the time, the dog will stay within 3 yards of the owner. All right, so based on this, what can we say about the location of the owner, right? So because we understand the behavior of the dog, and if we see the dog at the 30 on the football field, we can be 95% confident that the owner is between 28 and 32. Does the jump between these facts to this statement, are we all good with making this kind of leap here? We see the dog's at the 30, and we know, 95% of the time the dog stays within 2 yards of the owner. So based on that, I'm 95% confident that the owner is between 28 and 32. So, but the truth is that the owner could actually also be at, say, 32.5. It could even be at 33.5, could be even farther away than 3 yards from the dog, or the dog could be more than 3 yards from the owner. That would be surprising to us, because that means that this picture was taken, just happened to be taken at one of those rare moments where the dog chose to be more than 2 or 3 yards from the owner. It happens, not very often, but it happens. And we would just be like, oh, well, that's a coincidence that this picture was taken at that moment. Okay, so what's the point of this dog and the owner thing is that this is the idea of seeing the location of the dog, but not knowing the location of the owner is kind of like seeing the mean of a sample, but not knowing the location of the population mean, okay? And from the central limit theorem, we know that the location of the sample mean generally lies close to the population mean. So like the invisible owner, the location of the population mean is unknown to us, right? The population is so big that we can't observe it directly. So we can't get the mean of the population directly, right? That the mean of the population is unknown to us. And on the other hand, the sample is observable by us. And so we know the mean of the sample. The sample mean is known. That value is known to us. Okay. And according to the central limit theorem, the sampling distribution of y bar, the location of y bar, generally remains close to the mean of the population. That was kind of all of these simulations that we did, all of these little graphs that we'd shown here, was that the mean of the population, the mean of the sample is usually pretty close to the mean of the population, so much so that it follows the normal distribution. And because it follows the normal distribution, we can see 95% of the time, y bar is going to be within 2 standard errors of the mean mu. And so because we understand the behavior of the sample mean y bar, when we see the location of the sample mean y bar, we can be confident that the population mean mu is close by, right? We can be 95% confident that mu is within 2 standard errors of y bar. There's a question in the chat. It says, why don't we just use 99.7? Why don't we go out 3 standard errors? Okay. And that's a valid thing. And if you wanted to be 99.7% confident, you could go 3 standard errors. It's just that when you go out too many standard errors, your interval becomes less useful. And I'll give you some examples of that later. But that's a good point. We can have higher levels of confidence for, by making a wider interval, but often wider intervals are less useful to us. Okay. All right. So I hope this statement is okay, that because we know the behavior of y bar when we talked about sampling distributions, when we see some value for the sample mean, when we say, the mean of my sample of 30 butterflies or of 16 butterflies has a mean of 30 square centimeters, we can be confident, 95% confident, that the mean of the population is within 2 standard errors of y bar. Do we feel okay with a statement like that? I hope. All right, and so we're going to say I am 95% confident that the population mean mu is between, we're going to take the sample mean y bar and we're going to go down 2 standard errors, okay? And technically, a number that's more precise than 2 is 1.96. Each standard error is sigma divided by the square root of n. So we're going to say that mu is between, this is basically y bar minus 2 standard errors and y bar plus 2 standard errors. All right, so this is like, we're making some leaps here, and I hope, do we feel okay about this kind of statement here? We're going to say, because I've seen the location of the sample mean, it's right here. I'm now confident that the mean of the population, which is unknown to us, is going to be between, y bar minus 2 standard errors, technically 1.96, and y bar plus 2 standard errors, or plus 1.96 standard errors. Okay, is this okay with everybody? Thank you for nodding your head. There is an issue though, okay? And that is, we don't know what sigma, the population standard deviation, is, right? So the whole point here is, like, we don't know what the population mean is, and so we're using a sample and the mean of the sample to make estimates about the population mean. And I can't think of a scenario where you don't know the mean of the population, but you do know the standard deviation of the population, right? This seems like this. If you don't know the mean of the population, how are you supposed to know the mean of this standard deviation of the population? I suppose there's some strange scenario where this could be the case, but in general, we're not going to know what the standard deviation of the population is. So what do we do? What do we do? I don't know the population standard deviation. So, well, we're going to do the best we can, which is really what all we can do every day, is the best we can with what we have. And we're going to say, well, if I don't know the standard deviation of the population, the standard deviation of my sample, that's probably a decent guess, decent estimate for the population standard deviation, right? So population, this big entity, I don't know exactly the standard deviation of everybody in the population, but here's my sample. Within my sample, the standard deviation of my sample is like, what, 7, 3, whatever, some number. That's got to be a somewhat decent estimate of the population standard deviation. If this sample is supposed to be a random sample representative drawn from the population, the standard deviation of my sample should be somewhat of a good guess for the standard deviation of the population, okay? So we're gonna say, all right, let's go ahead and do that. And we're gonna say, all right, my estimated standard error is going to be S divided by the square root of n, right? So rather than the standard deviation of the population, sigma divided by the square root of n, which is our standard error, we're going to just estimate it. And we're going to take the standard deviation of our sample divided by the square root of n. Okay. And this is, I think, a reasonable thing to do, but it does add a layer of uncertainty in our calculations, all right? Because now we don't know if my standard deviation of my sample, is it too big? Is it too small? Okay. Is it a good number? Is it a bad number? We don't really know. We're just hoping, you know, like everything else, we're just hoping that what we have is good enough. So, so what could happen is that, you know, if your standard sample's standard deviation S is too small, your resulting confidence interval could end up being too narrow, right? So you're supposed to say, you know, I want to go up or down 2 standard errors, but now your estimate of the standard errors may be too small, and that could lead to a confidence interval that is too narrow, and that could end up leading to the wrong conclusion. So, so what we're going to do is, and it just seems like, this seems like a whole series of unintended consequences, but mathematically it all works out, is that we're going to just kind of, you know, fudge our numbers a little bit, right? So we're going to say, all right, my sample standard deviation is this, and I don't know if it's too big or too small. So just to kind of factor in a little bit of a cushion, instead of going up or down 1.96 standard errors, let's just kind of nudge that number, and just for a little bit of safety, let's increase it to say 2.1, okay? And we're gonna just use a bigger number. All right. And maybe you feel okay with all of this that I'm saying. Maybe it doesn't feel that great, but mathematically it kind of works out. And so what number should I use? Like, do I push it from 1.96 to 2.1? Do I push it to say 2.2, 2.3? What number do I use? And so the answer is going to come from a distribution called the t distribution. And the t distribution looks a lot like the normal distribution. It's just, it looks like it just got squished and widened out a little bit. And we say it has thicker tails because the pointy ends on the sides, those are a little bit thicker and wider, okay? So when we say my sample has a standard deviation, and this is going to be a good estimate of my population standard deviation, the size of our sample is actually going to play a role in kind of the number that we're going to use. So the idea again is, instead of going up or down two standard errors, we're going to just kind of fudge that number and say, all right, instead of 2, we're going to bump it up to 2.1, maybe 2.2, a number a little bit bigger. Now, how much do I need to kind of to fudge that number? How much do I need to kind of increase that? Is going to depend on my sample size. If I have a very big sample, right? Let's say I've got like 1,000 values in my sample, then the standard deviation I get from my sample, I can expect to be a pretty good estimate of the population standard deviation, right? So the population standard deviation is some unknown value mu, but if I have like 1,000 values in my sample, I can say, you know what? My sample standard deviation, it's got to be pretty good, right? So rather than, changing the number drastically, maybe I'll only adjust it a tiny bit, right? Maybe I'll go from, so the true number is 1.96. Maybe I'll go from 1.96 to say 1.99 or something like that. Okay. On the other hand, if I have a very small sample, okay, let's say I have 5 people in my sample. Okay, if I'm estimating the standard deviation based on a sample of 5 people, my standard deviation estimate could be wildly off. It could be like way too big, way too small. I can't expect the standard deviation based on a tiny sample to be that reliable as far as being an estimate of the population standard deviation, right? Does that kind of make sense? If our sample size is small, our standard deviation might be a bad estimate of sigma. And so to kind of compensate for this, we're going to fudge our number. Instead of 1.96, we're going to bump it up to something a lot bigger, say 2.3, okay, 2.365. This is what we would do if we have a small sample, because we can't expect our small sample to be a very reliable estimate of the population. So we're going to do that, okay? And so this gets taken into consideration in this term called the degrees of freedom, okay? And the degrees of freedom is found by taking our sample size n, we subtract off 1, and that becomes our degrees of freedom. df is equal to our sample size minus 1. And as the degrees of freedom approaches infinity, then the t distribution values match the normal distribution, the z distribution, and we would use 1.96 for a 95% confidence interval. There's an interesting history behind the t distribution. The t distribution was developed by this quality control engineer, William Gossett, who was an employee of Guinness Brewery, the beer factory in Dublin, Ireland, and he was kind of testing batches of beer, and during his work, he would reject samples of beer, and they would do further testing, and they say, you're doing something wrong with your math, and so he went back and he studied it, and he realized, the problem was he was using the normal distribution, and he realized he had to use something other than the normal distribution, and he developed the t distribution. And so anyway, interesting story. You can watch these YouTube videos about it. You can read up on Wikipedia and things like that. Okay, this is what your t table looks like. This is also available in the reference tables PDF. So after the normal distribution, if you keep going to the next page, table 4 is critical values of the student's t distribution. And this is what we have. And so you can see at the very bottom, it says confidence level 95%. And right above that, you have 1.96. That would be what we had if you have infinity degrees of freedom. And again, if you have a very large sample, say like a 1,000 observations, 1,001 observations, so you have 1,000 degrees of freedom, the amount you have to kind of adjust is very small, going from 1.96 to 1.962. But as your sample size gets smaller and smaller, and you have fewer and fewer degrees of freedom, so if you have, say, a sample size of 5, you would have only 4 degrees of freedom, and your number is much bigger at 2.776. Okay, so as your sample size increases, you have more degrees of freedom, and the amount you kind of have to compensate, and the amount you have to adjust that number from 1.96 to something bigger gets, you have to kind of adjust it less, right? Well, if you have only 1 degree of freedom, meaning your sample size is the size of 2, your compensation factor has to be much bigger, 12.7. I would not recommend trying to do a confidence interval based on a sample size of 2. It's just probably not a good idea. Okay, so let's try this out. Okay, so if we take everything into kind of consideration, we make this formula. Oh, so what are the numbers at the top? The numbers at the top, and this will come in later when we do t-tests. So at the bottom, we have 95%, and that's because you can imagine shading in the middle, 95%, okay? So it says, all right, let's say we want 95% in the middle, 0.95. How much is going to be in this tail? You're going to have 2.5% over there and 2.5% there, right? And so if you look at 95%, the corresponding top part, this upper tail probability, is going to be 2.5%. Okay. And if you're going for like the middle 80%, okay. Oops. If what you're going for in the middle is 80%, this is a bad picture, you'd have 10% over here and 10% over here. So if you look at 80%, you go all the way to the top, it says the upper tail probability is 10%. So that's what these numbers are corresponding to. And they're saying, you know, if you only look at one tail, so you know, we call this would be the upper tail. And this would be the lower tail. Okay, so you have this in your upper tail, and that's basically what we're saying. All right, so we got, so most of the time we're looking at 95% confidence intervals, but you know, you can make other confidence intervals. You can have a 90% confidence interval. You can have a 99% confidence interval, things like that. And 95% confidence corresponds to 1.96. If you have infinity degrees of freedom, and if you have fewer than that, which is every other scenario in real life, you got to use a number that's a little bit bigger than 1.96. And so when we create our formula, we're going to say, you know what, when you take a sample, your sample has a mean y bar, right? This is like observing the dog at 30. You know, where can we be confident that the owner is, or where can we be confident that the mean of the population is? Well, it's going to be between basically plus or minus a number of standard errors. And so we're going to say, all right, how much do I go up or down? Not exactly 1.96, some other number, and that number is going to come from the t table, and we're going to say that's this t star value coming from the t table, coming from some column here. And we're going to go multiply that by s divided by the square root of n, being the standard error, or estimate of the standard error, the standard deviation of our sample divided by the square root of our sample size square root of n. Okay, this whole quantity over here, this is known as our margin of error, right? So sometimes you hear that. Let's see, you know, so-and-so is leading the polls with 52% of the vote with a 3% margin of error or something like that. Okay, and that basically just means you're going to go plus or minus some quantity here. All right, so let's do our butterfly example again, and we'll just do something a little bit more, maybe some more precise values. And we're going to say we got 14 random butterflies. We measured their wing areas, and we're going to say the mean of our sample of 14 butterflies is 32.81. We have a standard deviation of 2.48. All right, and we want to make a 95% confidence interval. Okay, so our sample mean, our y bar, 32.81. The standard deviation of my sample is 2.48. My sample size is 16. Okay, so my confidence interval is y bar plus or minus t star times s over the square root of n. Okay, so to find our t value comes from the table.
Sorry, Professor.
Yes.
Isn't sample size 14?
Oh, you are absolutely right. Thank you for catching that. Okay, so my sample size is 14. Thank you. Sample size is 14. We're going to go to the table, and we need the degrees of freedom. Degrees of freedom is n minus 1. So we have 13 degrees of freedom. Okay, so we go to the table, we're gonna make a 95% confidence interval. So we go to this column, 95% confidence. We're gonna go to 13 degrees of freedom. 2.160, I think, if my eyes are not playing tricks on me. 2.16, 95% confidence. So my T star is gonna be 2.160. All right, so now it's just a matter of kind of plugging in numbers. 32.81 plus or minus 2.160 times S 2.48 divided by the square root of 14. Okay. Let's pull up my calculator. If I can find it. Here it is, I think. Okay, so we'll do 32.81 plus 2.16 times 2.48 divided by square root of 14. Okay, and this gives me 34.24166. Okay, so on the upper side, if I do the plus, I already forgot my number, 34.24, let's just do 242, 34.242. And then on the lower side, we're going to do, instead of the plus, we're going to do a minus. And I get 31.378. Okay. Okay. And that's that. That's our confidence interval. All right. So I think I plug all of this in and I get 31.378, 34.242. So this is the results on this slide here. So far, so good? All right. Okay, so the statement that we would make is we are 95% confident that the mean wing area of all monarch butterflies, so that is the mean wing size of all the butterflies in the population, if we somehow were able to, this is a ridiculous idea, but somehow like freeze time, go out butterfly hunting, catch every single butterfly in the universe, and then we measure every single wingspan of all the butterflies out there, and then we calculate the mean. We say, all right, now I have captured the population, and I've captured and I've measured every single butterfly, and I've calculated the mean. It took me, it took everything I had. There was 9,875,000 butterflies, and I got them all. And I measured every single last one, and I got the mean. And I'm saying, basically, I don't want to do that. And I'm saying, you know what? I'm pretty confident. I'm 95% confident that if we were to go through that painful process, that the mean would be between these two numbers. Okay, I could be wrong. I'm 95% confident, meaning, I give myself a little bit of 5% room to be wrong. I'm going to say, I don't want to go through the process of hunting every single butterfly, putting them into extinction and getting the wing area of every single one, just to find, some number when I can say, yeah, it's probably something around here, between 31.3, 34.2. This is good enough for me. Okay, so how can we make some interpretations here? All right, so someone asks, do we have evidence that the mean wing area is different from 31 square centimeters, 31.0, right? So I'm 95% confident that it's between 31 point, let's just say, call it 31.4 and 34.2, all right? Let's just keep it simple numbers here. 31.4 and 34.2. Is it different from 31.0? Well, we're going to say, well, 31.0 is less than the lower end of my interval, right? So if we're looking at some number line, so here's my number line. Here's 31.378. Here's 34.24. And basically, I'm confident that it's in here. Like this is my 95% confident, right? 31.0 is like over here. This is 31.0. This is outside. This is outside of my interval. Okay. So 31.0 is outside of my interval. And I would say, yeah, it's not between 31.378, not between that and 34.242. So I'm going to say it's not what we would say a plausible value. I would say I'm pretty confident. I'm confident I would say I have evidence that the mean is something other than 31.0, right? I'm confident that the mean is between 31.378 and 34.242, some value in there. I don't know exactly what it is, but it's likely to be some value in there. And we're going to say, yeah, I'm pretty sure it's not 31.0. Okay. Do we have evidence that the mean is different from 34.1? 34.1. So if we look at this picture, 34.1 is inside my interval, right? 34.1 is somewhere around here. It's between this and this. So 34.1 is inside. And we would say no. Do we have evidence that it's different from 34.1 square centimeters? And our answer is no. 34.1 is between the ends of our interval. So this would be considered a plausible value. Like it could be. I'm sorry, is there a question? Oh, maybe we just accidentally unmuted. No problem. All right. So we're going to say, so we're not going to say that we have evidence that the mean is different from 34.1. Okay. Can someone say we have evidence that the mean is equal to 32.2, right? So we look at our interval and we say, oh, 32.2, that's somewhere in there, okay? Here's 32.2, I don't know, somewhere inside there. All right, but the problem here is we can't use a confidence interval to say that the value is equal to some particular number, right? So 32.2 is inside the interval. It's a plausible value, but we can't use our confidence interval to say that it's exactly equal to 32.2. So, so again, if you think about like the dog and the owner, right? So if you see the dog at 30, you know, someone says, you know, could the owner be at say 26? And you go, no, I'm pretty sure that the owner's not at 26. Okay. Could the owner be at 33? Or I mean 30, 31. If the dog's at 30, you go, oh, I guess the owner could be at 31. Could someone say the owner is definitely at 31? And the answer is no, I don't know, right? If the dog's at 30, is the owner definitely at 31? And the answer is no, we don't know exactly where the owner is. We're just pretty confident that the owner is like within 2 yards of the dog. And similarly, when you create a confidence interval, you can just say, I'm pretty confident that the mean of the population, mu, is between here and here, but I don't know exactly where it is. All right, so these are similar questions, but you know, the answers and the interpretations are, you know, slightly different. I want to make sure we're okay with the statements that we're making here. All right, okay. All right, and so, you know, we had this question, you know, why don't we just use a 99.7% confidence interval? Like, why don't we just try to be like super confident, right? So the confidence level says how confident we are that the population mean mu is within the bounds of the interval. And if we want to be more confident that mu is inside the interval, we can just make the interval wider, right? Like if I see the dog at 30 and I want to say, you know, where's the owner? I can just be like, oh, I'm 100% confident that the owner's between, you know, 0 and, yeah, I guess on a football field, it goes to 0, you know, 0, whatever, 0 and 50, right? I'm very, you know, because the leash doesn't stretch that strong far. So I can be very confident that the owner, but that's not useful, right? Generally, we want a narrower interval. Narrower intervals are generally more useful to us, but it comes at the cost of giving up confidence, you know? So for example, if we're thinking about like, you know, what's your income going to be next year? Because you need to make a budget, right? You need to make a budget for how much money you can spend on food and entertainment and things like that, or whatever. And you say, well, what's your income going to be? Okay, and you know, let's say you know you're in some industry, like you're a salesperson that works on commissions or something, and you can be like, you can you know facetiously say, you know, I'm 100% confident that my income is going to be between $0 and $1 million next year. All right. Okay. Is having an interval that wide going to be useful as far as setting a budget? No, it's not. Okay. Having an interval super wide like that, that's not going to be useful as far as creating a budget, because it's too much. Okay. On the other hand, you can make a much more narrower interval. You can say, yeah, pretty confident I'm going to have between $70,000 and $75,000 in commissions. And then with that, you can create a budget, right? You can say, you know, it's going to be between this and this. Having a narrow range, you can make a pretty precise budget. But if you make your range too small, you could also end up being wrong, right? If you say, oh, I'm pretty confident it's going to be between 70 and 75,000, it's quite possible that you mess up and you end up having less than that or more than that and things like that. So that's the trade-off. Usually a narrower interval is more useful, and that's why we don't go for 99.7. We usually go for like 95%, because that kind of represents, you know, maybe this balance between, you know, we're still pretty confident, but our interval is not getting too wide. Okay. I don't have any of you guys done like 23andMe? You looked up your things. So if you go on like 23andMe, there's this little thing at the very bottom, and it says, you know, we're only 50% confident in these values that you're giving you, right? So it's like I participated in 23andMe, you know, I spit in this little thing and I mailed it in, and they said, oh, you're Asian. I was like, oh, okay. But it says, you know, we're only 50% confident. And if you crank it up to say 90% confident, right? So 50% confidence is like, you know, you're this much Japanese and this much, you know, Chinese and Taiwanese and things like that. And, you know, that was 50% confident. But then if you crank it up to say, you know, I want you to be 90% confident, then it just becomes very broad. And you're just like, oh, you're some kind of Asian descent, and basically it's not as interesting or useful if you have if you need to be kind of conservative and safe in kind of the interval that you're making, right? So usually a narrower interval is more interesting, it's more useful, but you're going to be a little bit less confident in it. Okay, so 95% is kind of the number that a lot of people end up using. But yeah, for depending on your circumstances, you can have a narrower interval, say 90%, 80% confidence interval. Or if you want to be kind of safe and cautious in the interval that you're making, you can make it wider and have a 99.5% confidence interval, but it's going to be a lot wider. Okay, let's take a couple look at these examples here. So when we made a 95% confidence interval, the resulting confidence interval is 31.378 to 34.242. And let's say I took the same exact data and I made a 99% confidence interval. Okay, with the same exact data, my Y bar is exactly the same. My S and my square root of N, that's exactly the same. The only thing that changes is to go from 95% to 99%, I'll go from 2.16 to 3.012. So here is 95% at 13 degrees of freedom. My number is 2.16. And 99%, 13 degrees of freedom, your number is 3.012. That's the only thing that's going to change, okay? So the only thing that changes is this value, T star, and that's going to change the margin of error. The margin of error goes from 1.432 to 1.996, and this results in a wider interval. You increase the level of confidence, you're basically casting a wider net. You're saying, you know, I want to be sure to catch the population mean inside this net. So if you want to be more confident, you just cast a wider net, and this is what we end up getting. Okay, but this is interesting here. Okay, so my confidence interval here goes 31.378 to 34.242. This one goes from 30.8 to 34.8. So with our 95% confidence interval, we ask this question: do we have evidence that the mean in our population is different from 31? The answer there is yes, 31. But we looked at our interval. 31 is not inside our interval, right? My interval goes from 31.378 to 34.2. 31 is outside of that range. So we say, yeah, I'm confident that it's not 31. Okay. With a 99% confidence interval, my interval goes from 30.8 to 34.8. And now we ask the same exact question: do we have evidence that the wing area, the mean wing area in the population, is different from 31? What's our answer now? Our answer now is no, because 31 is now inside the ends of the interval, right? My interval goes from 30.8 to 34.8. And so now 31 is inside the interval and it's considered a plausible value. And we say, we can't say that we're not going to say that we have evidence that mu is different from 31. So same exact data, same question, and we're coming to like opposite conclusions. Do we have evidence that it's different from 31? Over here, my answer is yes, and over here, my answer is no. Are these answers in conflict with each other? What do you guys think? How do we explain the different conclusions? Well, the different conclusions come from the fact that we're using different levels of confidence, right? So this first one, we are 95% confident in our answer. In the second one, we're 99% confident in our interval, right? So basically, if we want to be, the second one, we're just being a little bit more cautious. Okay, the first one, we're 95% confident, which gives us kind of 5% room for error. And the second one, we say, you know what, that's a little bit too much risk for me. I want to be more cautious, right? So it's kind of just like eliminating options, right? So if you're going to say, you know what, I don't know, imagine you have to keep different, I don't know, clothing sizes in your closet for like different people that might show up. And you say, well, you know what, this is taking up a lot of space. Can I throw out some of these things, right? Like, are we ever going to get somebody this big or this tiny or something like that? And you go, you know, someone could be like, you know what, I just want to play it safe and I want to make sure that we have, you know, a costume that's going to fit, you know, really tall people and really short people. So I don't want to throw anything away, right? Somebody else goes, yeah, you know what, you're probably right. Let's go ahead and throw away some of these extreme sizes or something as far as the costume closet goes, right? And so two people can have kind of the same idea of the data, but because they have different risk tolerances, they might end up making different conclusions. And this is basically what's happening here. We've got, if you are okay with being only 95% confident, you're willing to just kind of throw away the possibility that the mean is 31, because you look at your interval and go, you know what, 31's outside of this thing. I'm willing to kind of throw away that possibility. Someone who wants to be 99% confident is a lot more cautious and says, you know what, just to be as safe, I'm not ready to eliminate 31 centimeters as a possibility. That this is 31 square centimeters is still a possibility for the for the population mean. I'm not ready to kind of eliminate that. So we're going to just play it a little cautiously. And we're going to say, you know what, it's still a plausible value. Does that make sense as far as why we're arriving at different conclusions, even though we're looking at the same data? It's just the different level of confidence can lead us to different conclusions here. Okay, all right. Well, thank you for the one thumbs up there. Let me go ahead and give you your last view quiz answer for today. Today's last view quiz answer is the letter E. E as in elephant. E as in elephant. It's your last view quiz answer. Oh, okay. So this is one thing that that we have to be careful about. So far, the statements we've been saying are something like, I'm 95% confident that the mean wing area of monarch butterflies is between, you know, these two numbers, 31.378 and 34.242. Okay. This is different from saying this, and these almost sound exactly the same, but here I'm using the word probability. It would be wrong to say there's a 95% probability that the mean wing area of all monarch butterflies is between 31.378 and 34.242, right? So one is saying, you know, I'm 95% confident, and I'm saying that's allowed, but the other one we're saying there's a 95% probability, and I'm saying that's not allowed. Okay, so what's the difference? Okay, let me do this little coin flip example. So not a trick question. Here's a coin, here's a quarter. I'm going to flip it. And the question is, what's the probability this is going to land heads? Okay, not a trick question. The answer you guys would say is what? 0.5. Okay, all right, so I go ahead and I flip it. Now, the coin is here. And the question now I'm going to ask is, what is the probability that the coin has landed heads? What is the probability that the coin has landed heads? What do you guys think? Okay, well, thanks for playing along. Okay, all right, and I'm looking at the coin now. You guys can't see it, all right? And I cover it back up, and I ask the same question. What is the probability that the coin has landed heads? What do you guys think? Anybody? What is the probability that the coin has landed heads? Okay, so a lot of you guys are writing 0.5, and I appreciate you guys doing that. But the answer is the last two questions were actually nonsense questions. We can talk about probabilities for events with uncertainty. Before I flip the coin, it is valid to ask, what is the probability that the coin will land heads? Okay, and it's correct to say that the coin will land heads with probability 0.5. However, once the coin landed, the question of what is the probability that it landed heads, that's a nonsense question, okay? There's no probability anymore. It either landed heads or it didn't land heads. There's no uncertainty. Something happened. So asking the question, what is the probability that it landed heads? That's actually a nonsense question. You don't know how it landed. You don't know how it landed. So you can say, I am 50% confident that it landed heads. You're allowed to say that. But to say there's a 50% probability that it landed heads is actually a nonsense thing to say, because there's no probability. It either landed heads or it didn't. Okay. And so similarly, when we're talking about the mean of the population, right? The mean of the population we're treating it as some fixed value. Like if I, again, were to freeze time, go on some butterfly hunting mission, capture every single butterfly, all whatever, 100 million of them, and I measure every single wingspan or wing area of the butterflies, and I find every single last one, and I calculate the mean of all of these things, there's going to be an exact mean value for the population of butterfly wing area, right? And it's going to be some exact value. There's no uncertainty associated with it. It's just some set value. We don't know what it is, but it's incorrect to talk about the probability that this quantity is between the here and here, okay? All we're saying is that, based on this technique of creating confidence interval, I'm 95% confident that it's within this range, but it's incorrect for us to say that there's a 95% probability that it's in the range. All right, I've got an example here. I think I'll let you guys kind of just work through it on your own as you go through the notes here. Basically, I don't know if you ever thought about this, right? Sometimes maybe as a kid, oh, maybe I was just a weird kid. You go to the grocery store and then you see like these bags of potatoes and they say, 5 pounds of potatoes. And I go, is this really 5 pounds of potatoes? And I was, as a kid, I was like, all right, I'm going to put these things in the scale. I'm going to choose the heaviest bag because I bet some of these bags weigh a little bit more than 5 pounds. Okay, maybe I was weird. But anyway, so let's say you went out and you got all of these potato bags and they're labeled 5 pounds. But then when you measure them on the scale, this one was 5.1 pounds, that one was 5.3 pounds, another one was 5.0 pounds and things like that. Based on this set of random bags, can you make a confidence interval for the mean weight of all bags of potatoes? Okay, I think I've got the work here. I hope it all kind of makes sense, and I'll let you guys work through that. But let's just call it a day here. Okay, so that will be it for today's lecture, and that will be it. So have a good weekend. Happy Independence Day, and we will see you guys next Tuesday. Don't forget to turn in your homework and don't forget to take your quiz. So you will see that. All right.
All right, Professor.
And have a good night. Yeah, let me go ahead and start the recording and I'll answer your questions.